الشبكة العالمية للعلماء الجزائريين إيناس هي منظمة غير ربحية تأسست عام 2016 من قبل أكاديميين ومهنيين جزائريين مقيمين في الولايات المتحدة الأمريكية. الهدف من وراء تأسيسها هو رد الجميل للوطن والمساعدة في رفع مستوى التعليم في الجزائر. مهمة إيناس هي ربط الكفاءات الجزائرية في جميع أنحاء العالم مع نظرائهم في الجزائر. من بين أنشطتها نظمت إيناس مؤتمراً مهماً عقد خارج العاصمة واشنطن في الولايات المتحدة الأمريكية عام 2019. حدد المشاركون في المؤتمر عدة قطاعات حيوية تحتاجها الجزائر، واتفقوا على العمل في 10 مشاريع تغطي مجالات مختلفة نذكر منها التعليم والرعاية الصحية والزراعة والسياحة البيئية إلى آخره. والعمل في هذه المشاريع لا زال قائما. تستخدم إيناس أكثر المناهج العلمية تطورا من أجل تسيير ومعالجة هذه المشاريع. البداية المتواضعة لإيناس تضمنت عددا قليلا من الأعضاء، وهي اليوم تضم مئات الجزائريين الأكفاء من جميع أنحاء العالم. هدفهم هو المشاركة في رد الجميل والمساهمة في بناء جزائرنا الجديدة. هذه الثلة من الكفاءات الجزائرية الفخورة بوطنها تجمع بين التنوع والخبرة مع الاستعداد والرغبة في تمهيد الطريق من أجل مستقبل مشرق للجزائر. تستخدم إيناس منصة تقنية جد متطورة تسمح للأعضاء بالتعاون وتبادل الأفكار والخبرات. كمنظمة قائمة، إيناس لديها أقسام عملية مختلفة تضمن الدعم المحترف لجميع أعضائها ومشاريعها وتظاهراتها العلمية. نرحب بكل الكفاءات الجزائرية في العالم للانضمام إلينا في هذه المهمة النبيلة. الجزائر أكبر منا جميعا، فلننهض ولنترك بصمتنا.
بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف المرسلين. السلام عليكم ورحمة الله وبركاته. مرحبا بكم معنا في لقاء جديد مع الشبكة العالمية للعلماء الجزائريين إيناس. معكم محمد عمروش. I am the group leader of the Geoscience group. واليوم إن شاء الله we will have another webinar related to the project Earthquake Hazard Mitigation. Donc هذا البروجي إن شاء الله on essaie d'inviter des spécialistes et des experts في الدومين تاع earthquake hazard mitigation and earthquake engineering, covering both geosciences and structural engineering. And each month we present a new idea or a new pattern of this discipline. So today إن شاء الله we are having the honor to have أستاذ عمر لاغروش. السلام عليكم أستاذ، مرحبا بك معنا.
السلام عليكم، أهلا وسهلا.
ربما بعض من المتابعين يعرفوا الأستاذ عمر لأنه he is already a member of INAS and vice chair إن شاء الله. So today he is going to talk about numerical techniques for earthquake engineering and structural dynamics. But before starting, I would like to briefly introduce Ustad Omar. So Dr. Omar Laghrouche is a professor in structural dynamics and vibration within the Institute of Infrastructure and Environment at Heriot-Watt University in UK. He obtained a PhD from École Centrale de Nantes in France in soil structure interaction problems applied to traffic vibration reduction. Then he moved to Durham University in UK, where he worked as a senior research fellow on novel numerical methods for wave problems. In 2004, Professor Omar joined Heriot-Watt University as academic with the civil engineering discipline. He is executive member of the UK Association of Computational Mechanics and a member of the General Council of the International Association for Computational Mechanics. Ustad Omar is also a fellow of the Institution of Civil Engineering, FICE, a fellow of the Higher Education Academy, and a member of the EPSRC, Peer Review College, which is, he is also subject editor to the Applied Mathematical Modeling Elsevier Journal, which is Impact Factor 5.12. The main thrust of his research has been the modeling of wave by efficient methods using numerical simulations. So Professor Omar Laghrouche is also vice chairman of our association INAS and currently active member in the project of e-learning, I believe. Inshallah, I didn't miss any part, Ustad Omar.
Okay, شكرا أخ محمد. السلام عليكم أيها الإخوة والأخوات اللي حاضرين معنا. It's really a pleasure for me to be here with you. As Akh Muhammad mentioned earlier, I'm a member of INAS, and I would like to share a bit of my academic work and research work with you. So let me share my presentation. Al-Akh Mohammed Amrouche asked me to present something in this group. So I was thinking what to present. It has to be linked to earthquake engineering and structural dynamics. So I thought probably I talk a little bit about soil structure interaction, and I hope it will be very useful and very helpful. كما سبق يعني قدمني الأخ محمد عمروش، أنا من حي الشعبي من بلدية الأبيار، تابع بلدية الأبيار في العاصمة، تما وين تربيت، تما وين قريت. رحت ليكول بوليتكنيك في الحراش، ومن بعد جيت لفرنسا درت DUA PhD وجيت لبريطانيا. ف I was a research fellow at Durham University, then I came to Heriot-Watt University. الأخ محمد عمروش he presented what I do currently. On top of that, I would like just to mention I am involved in ENAS. I'm lucky to be, in the board of directors, executive committee, and also I try to contribute in the education committee. وكل حاضرين هنا, you are most welcome to join ENAS and become active members. It's all for Algeria. يعني كل هذه المجهودات نحاول يعني نرد القليل من الجميل للوطن. ف I hope يعني some of you are already members and others will join in the future. So my teaching activities, I taught different courses in the past. So currently I teach mechanics, earthquake engineering and structural dynamics. I have to teach it according to Eurocode 8, and I do numerical methods in engineering. For research activities, Al-Akh Mohammed Amrouche, he already mentioned some of them. So usually for research activities, we don't do what we like. We do where we get funding. So وين يكونوا دراهم pour la recherche, donc on s'oriente vers هذوك يعني topics. Because you have to bring PhD students, you have to bring research associates to do the research. We cannot do it ourselves. We have to work with people. So this is what I did in the past. So soil structure interaction, why? Whenever there is something to investigate, we always discuss, shall we take the structure? Shall we include the soil? Does the soil have impact on the structure? And vice versa. Does the structure influence the soil? So the best thing to do is obviously to deal with the structure on its own, and then to include the soil and see, if the behavior is different. But also, for both options, there is a cost. There is, a cost for that. So taking the soil, it makes the problem more complex. It takes more time. And so many people say, if you don't know what's below your feet, how can you include that in a very sophisticated model? يعني بطريقة أخرى, you create a very sophisticated model, ولكن you don't know really what's in the ground, what's in the soil, what are the soil layers, what are the mechanical properties, what's the configuration. So we all know that soil is one of the most complicated media. فهنا نحاول يعني just to discuss that and give some examples, and then towards the end I show two methods I dealt with in the past to deal with soil structure interaction. And here I'm just giving photos to see what happened after earthquakes in terms of damage, and then we can see how the structures behave. Obviously, the structures, they were influenced by the soil, but has the structure influenced the behavior of the soil? And I know some researchers they go beyond soil structure interaction and they talk about structure, soil, structure interaction. So it means if you have a structure and then you have the soil, you will have soil structure interaction. But if you have more than one structure, you know, the structure, soil structure interaction can occur as well. So it means the presence of other structures can influence that soil structure behavior. So let me start with just a free field motion. So let's assume we have soil and you have some waves, you know, some seismic waves, you know, propagating in this soil medium. So there is no structure, so there is no soil structure interaction. So usually the field is, you know, taken ideal, like it's flat, horizontal layers. And in this case, you know, the seismic waves, they come from so far from deep in the soil. And then when they reach the surface, they basically propagate in a vertical path. And therefore, they are reflected in a vertical path. You know, it's ideal. However, if we have a structure, that behavior can be different. So the ground motion may be modified by the presence of the structure. Of course, dissipation of energy occurs, you know, through damping. And if the site is uniform, damping is prominent. But if the site is a layered site, or there is a valley, or there is a bedrock after, you know, a certain depth, you know, radiation damping is less prominent. And we all know that the waves can be trapped in the soil layers, specifically in the top layer if it's soft. And then, you know, it takes time for these waves to dissipate and they lead to large displacements at the surface. So these are the approaches we take. هدوما les approches اللي نديوهم. إما the structure is founded on solid rock, هذا the top figure. So in that case, we consider that here it's solid, it's fixed base, and therefore we study the structure. كما نعرفوا les méthodes اللي نستعملوهم في هذه الحالة هذه. They are, you know, well used in structural dynamics, earthquake provision, in Eurocodes. Usually in this case, we believe that the structure is on solid rock, okay? However, if the structure is founded on soft soil deposit, so in that case, the structure definitely will respond in a different way compared to the previous case. Okay, so if we compute the response of the structure on fixed base, and then you take the structure and you take with it a soil medium around it, in general, there is difference in terms of behavior. So the structure base will deviate from the free field motion. Okay, and the dynamic response of the structure will induce deformation in the supporting soil. فمعناها the soil will influence that structure behavior. It's no more like here on the fixed base, but also that structure, if it's heavy, if it's huge, it will influence the behavior, the local behavior of the soil in the surrounding area. الأخ محمد, you hear me properly? You're following, no problem?
Yeah, we can hear you. There was some sound lag, but it's fine now. I think it's okay. Please carry on, Ustad.
Okay. Yeah, please let me know if there is anything.
Okay, I will let you know. Thank you very much.
Yes, yeah. Okay, so let's assume the first case. The structure is on the fixed base. So personally, I teach earthquake engineering and I teach according to Eurocode 8. So I teach the students how to deal with the structure. So usually the easiest method is the pseudostatic analysis. So in this case, we assume the structure will catch, the first mode, and therefore we approximate that first mode like linear variation from the base to the tip of the structure, to the top of the structure, linear variation of the displacement. So in that case, what we do, we take the base shear force and we distribute it in a linear way, and then we analyze that structure using static analysis. Or another method used in Eurocode 8, it's the response spectrum analysis. So we use what we call design spectrum. We evaluate the natural frequencies of the structure, the natural modes, and then given these natural frequencies, we use the design spectrum to get the maximum accelerations, maximum displacements, and then we use mode combination, natural mode combinations to compute the total response of the structure or the total forces applied to the structure. So this is called the response spectrum analysis. Of course, we can use linear transient analysis. So for that, we need computer software, and we have to create a model. So that's available. We can use any commercial software which can do that. Also, we can use nonlinear pushover analysis, which is also a pseudostatic method. Also, if you want to push the model far, you can use nonlinear transient analysis, and in that case, you can use nonlinearities either from the behavior, the material behavior, or you may even include geometrical nonlinearities like large displacements, large deformations. So this is the structure when it's on a fixed base. Okay, so we're dealing only with the structure itself. So in general, this is the analysis we carry out. However, now, when do we have to use soil structure interactions? So if we have a problem, shall we just consider the structure on the base and then consider on a rigid base and then just consider the structure and then carry out the analysis? Or shall we introduce part of the soil? So in general, we think that soil structure interaction has little or no effect if the structure is a small one, it's stiff structure, or if the soil is stiff, for example, it's a bedrock, so it's fully justified to consider just that structure, or if the site is modeled as a half space. So in that case, the waves, the seismic waves, will reach the surface, they will be reflected, and then they will be radiating away towards, the soil to infinity. So in this case, we think that it's fine to ignore the soil structure interaction and just to deal with the previously mentioned methods. However, if the structure is heavy, so I will give later an example of really heavy structure, or if the structure is slender like a big tower, it has, for example, like Burj Khalifa, for example, if it was in active seismic zone, for example, that's a slender structure. Or if we have a bridge, a very, long bridge, for example, that's a slender structure. We need to include soil structure interaction. Also, if we have soft soils, so we all know that the seismic waves qui يلحقوا la surface du sol, they are reflected, but then when they go back, they meet, at the end of the soft soil, they meet, for example, an interface of an elastic medium, which is stiffer, So they are reflected again, and they keep going and coming back in that soft soil. So the energy is trapped there, and it leads, to elongated period and, large displacements of the structure. So in that case, soil-structure interaction is really important. Also, if we have layered sites where we have, layers, des couches du sol, وفي هذه الحالة, if we have steep change in stiffness, a soft layer, then a hard layer, then, even a harder layer. So if there is contrast in the layers, definitely we need to use this soil structure interaction, just because, it's a complex behavior. So I hope it's very clear where it's important to have this soil structure interaction, and where we can afford to say its effect is negligible, and therefore we don't need to include it. Okay, so now let's assume the soil structure interaction is very important. It has an effect on the behavior of the structure, and it has to be taken into account. So what can we do? So there are a lot of methods. If we take, if we go to references, to research references, there are, so many researchers developed, different methods. But if you go to industry, I think in general, at least the people I dealt with, they always go to a finite element package, and then they try to develop expertise there. And we'll see that the far field radiation is the most important part of that. So usually we have finite element method, and we have so many packages for that. We have, Abacus, ANSYS, SAP 2000, etc. We have boundary element method, BEM, finite difference methods, coupled methods, for example, finite element, boundary element, but also finite element, infinite elements. So it's a kind of elements we put on the boundaries to allow wave radiation to infinity. So there are so many methods, and so many researchers developed, non-reflecting boundary conditions. They call them quiet boundary conditions, transparent boundary conditions, absorbing boundary conditions. But the aim is really the same, which is when the waves hit the external boundary, they're not reflected. فمثلا في هذا المثال يعني في هذا الفيجر هذا اللي عندنا هنا, assume the waves, they come from, deep soil, they enter the domain here, they hit, the structure, the free boundary, and then they are reflected. If I put nothing here, they will be reflected, okay? They will be reflected back into the domain, and then the results, they will be erroneous. They will be, wrong results, okay? So they will affect the computation, and then what you get is not correct, because what you have energy trapped inside your computational domain, and it's it's there, it's not dissipated. However, if you put the right boundary conditions on the external laterally and then on the base, then if the waves are reflected, when they reach these boundaries, they are allowed to go outside the domain. Then in that case, that's the right modeling, and hopefully we can model the proper soil structure interaction in this case. So I would like just to show if, for example, I fix the boundary, assume I didn't put anything here on the boundaries, and I fixed it. What we notice, the waves, when they reach, that fixed boundary, it's reflected with opposite phase, and basically it doesn't represent the reality, okay? Because it's not fixed, okay? Also, if you leave it free boundary, so what happens? The wave is reflected with exactly the same phase, and also it's not free, because if you say it's free here, it means there is no material on the left, or here there is no material on the right, which is not true. The soil is semi-infinite, and you have material laterally, and then according to the depth direction. So really, the boundaries are not fixed and they are not free. And this is really the challenge when you try to deal with soil structure interaction. So you take your structure, you couple it to your soil, but the soil is semi-infinite. It goes to infinity, you know, in certain directions. And in that case, you cannot take it all. What you take a chunk of that soil, a finite dimension. But when you take a finite dimension, you need to put the right boundary conditions. So I hope I described, you know, the big challenge. So using finite elements, for example, we know what to do inside the domain. We have, you know, elements, you know, linear, quadratic, etc., 2D, 3D. So, and then for the structure, it's the same. We have like brick elements, we have beams, columns, etc. So we can do that, no problem. But when you reach this boundary, this is the challenge. And when we deal with soil structure interaction, usually we spend more time dealing with the boundary condition to make it effective than we spend, you know, building the model inside. I hope I communicated this well, because that's where people spend a lot of time. Dr. Mohammed, are you following? And I hope the others are following as well. I'm not
yes,
talking
yes, please go ahead, Ustad. Very
yeah,
good.
okay, excellent. Yeah. So very quickly, I'm going to show two examples. So the first one, it's frequency domain analysis, and the second one, it's time domain analysis to deal with soil structure interaction. For time domain analysis, it's easy to understand because usually it's, you know, we have a finite element mesh grid, and then we divide our time into time steps, and then we have a certain scheme like explicit time stepping. And then, you know, for each time step, we carry out a certain analysis, we move to the next time step, etc. So it's easy to understand. However, we'll see it's an expensive tool. Frequency domain analysis, on the other hand, we take, you know, the forcing term. In this case, it's like the earthquake, for example. We carry out an FFT. We take, you know, the different signals we get from there, each signal with a prescribed frequency. And then for that frequency, we can carry out a frequency domain analysis. And then if you want to find the total response, you can recombine these responses obtained from each frequency. So first example, assume on the left, top left, you have, you know, semi-infinite soil, where you have, for example, a tunnel, pile, foundation, and you have some structures at the surface, and you want to model that, including the structures you have there. So as we mentioned earlier, this goes to infinity, so you cannot consider all that, so you just choose this rectangle, for example. And in this case, we assume that, you know, below this, you know, depth, we have a rigid bedrock, so it's really stiff bedrock. So we can afford to assume that, you know, at this bedrock we have fixed boundary conditions. However, laterally they are not fixed and they're not free. In the surface they are free, where you don't have a structure, but laterally they are free boundary conditions. So really you need to allow the waves to go to infinity without reflection. So any wave coming inside the domain, they should be able to leave these boundaries without reflection. So what we do, we build a finite element model. Here it is. So the part which has the structures, you know, it's meshed into elements. So I just show here squares or rectangles just to say these are finite elements. And then here, the bold line, the boundary conditions are fixed. And laterally, we put some boundary conditions to allow the wave to go to infinity. Okay? So what we do, inside, it's known technology. It's finite element. Either we code it or, you know, we use a software, so we know what to do inside for finite element. However, what to do on the lateral boundaries, That's what we don't find in commercial software, and you have to code it yourself. So for example, here, I give an example of absorbing boundary conditions. They are called consistent transmitting boundary conditions. I'm not going to give you a lot of maths. I'll give you just this and probably the next slide, and that's it. It's just to give you the idea, how, we build that. And then, the technicality of that, I think we can go to references, have a look at them. But the basics is this. On the boundary, for example, we take the right boundary, the right boundary here, okay, or here, and we assume that the waves, they come like a plane wave, okay? So usually the wavelength is large and it hits that boundary. In this case, the wave will be horizontal, okay? So if it's horizontal, I can write it using this expression to say that the wave is propagating along the x-axis, okay? It's a fair assumption. If the wave, comes from far and then it reaches that boundary, usually it's a plane wave, and in this case, it propagates in horizontal direction. So I can afford to do that. Here, it's just to say this wave is according to one of the frequencies from my FFT I carried out earlier. But now, along the depth, what we do, we take each layer of the soil, we divide it into sublayers, نقسمهم لديكوش صغار. But what's the thickness of that layer? It has to be the Rayleigh wavelength divided by 10, for example, because we know we have the pressure wavelength, the shear wavelength. The Rayleigh wavelength is the shortest one. So if I take the element to be, for example, that Rayleigh wavelength divided by 10, I can represent the wave pattern of the Rayleigh wave, but I'm sure I will represent the shear wave and the pressure wave because their wavelengths are even larger. Okay, so if we do that, at least a tenth of the wavelength, it should be fine. So we do it for each sublayer, and then we'll have as many sublayers as we wish. And then we do the assembling. We end up, so really the problem, it's a dynamic problem. We can use, for example, the virtual world principle, for example, or any other method. What we end up with a second order eigenvalue problem, for example, in this case of consistent transmitting boundary conditions. So we change it into a first order eigenvalue problem, but in that case, you double the size, and then you solve the eigenvalue problem. You get the eigenvalues, which are really eigenfrequencies. You get the eigenvectors, which are really eigenmodes in this case. And then you combine the solution, because here we assume everything is linear. So we can combine the solution using all eigenfrequencies and all eigenmodes. And we assume that's the solution. We replace it. And then what we get the displacement on the left-hand side, the left lateral boundary, and the displacement on the right lateral boundary as a function of a certain matrix R. When you multiply that matrix with the displacement, you get the forces you apply on the right-hand side and the left-hand side. So basically, we calculate the forces you put on the left-hand side and the right-hand side to replace the infinite side, which goes to infinity on the right, and the infinite side, which goes to infinity on the left-hand side. If you put these boundaries here, then you are sure the waves will be absorbed to go to infinity without reflection. So the expressions look like this, where H will contain and H dash will contain, the eigenfrequencies. V and its inverse will contain the eigenmodes. D and A, they are really about the geometry and the material properties of the soil. And then when you include these two matrices in your global system, So really in your global system, you'll have the mass matrix, the stiffness. In this case, we take hysteresis damping model. So if you include these in your system, because the displacements are unknown, so you will allow the waves to go to infinity. So here, we just put a forcing term. That forcing term can be an earthquake. But in my case, we developed these tools, but we had contracts, we had research projects dealing with traffic-induced vibration. So we just used traffic-induced vibration there rather than, a model dealing with earthquake seismic waves. So just to show you how we validate such models. So for example, if you take a soil model and then you calculate the displacement at the surface for a given forcing term, if you put the reflecting boundary conditions, you get, for example, this curve for vertical displacements, the continuous line. If you don't put the non-reflecting boundary conditions, you get the dashed line, and you can see it's different, okay? So the dashed line, it's a bit broken because they were reflected waves. However, the continuous one or the black one, it's smoother, so we can see the wave pattern there. And normally, it allows waves to go to infinity. And the other way to check that, what we do, we take, for example, 4 wavelengths of soil, and then we take 8 wavelengths of the soil, and then we take 10 wavelengths, we increase the size of the domain. So normally the results we find must be the same, because it doesn't matter how big is your domain, the waves that will be leaving your domain anyway. So it means the result must be the same. So that's what we did here. And we can see that the results, either a domain of 4 wavelengths size, or 8 wavelength size, or 10 wavelength size, the results are really similar. They are the same. So what it means my non-reflecting boundary conditions, they work fine. معناتها les conditions aux limites اللي حطيت latéralement يخليو الويفز هذوك يروحوا الانفينيتي. they are not reflected, ما يعاودوش يوليو. et donc les résultats اللي يكونوا عندي في لا سيرفاس تاع لو سول مثلا سي لي ميم. ندي ان سول تاع 4 longueurs d'onde 8 longueurs d'onde ولا 10 longueurs d'onde, ça fait pas de différence parce que هذوك les forces اللي حطيت latéralement يرومبلاسيو لو سول اللي يروح للانفينيتي. Donc I hope this is clear. Also, a way to validate this is, for example, to calculate the natural frequencies of the soil. So we know how to do that. We have analytical models to compute the natural frequency of the soil overlaying a bedrock. So in this case, for example, we used undamped model for a certain soil. So we looked for the natural frequencies for the horizontal and vertical vibration. So we got, for example, around 0.5. Of course, we got them here in terms of critical depth, so critical thickness of the soil. And we can see we're getting between the top one and the lower one. So the top one are the semi-analytical, and the lower ones are the numerical. And we can see we are getting the same critical depths, or in other words, natural frequencies of the soil. So this is another validation. I hope it's clear, because a soil layer overlaying a bedrock has many natural frequencies. But if you fix the frequency, you can study it in terms of critical depths. So it will have a lot of critical depths. So we can see here the critical depths between the numerical and the analytical. They are pretty similar. So كما قلت من قبل, I did get some projects in the past. I did it with research associates and with PhD students. It was dealing with traffic-induced vibration rather than seismic waves. So the models are exactly the same. It's just the forcing term will be different. So if it's seismic waves, we'll have, the forcing term will be the mass times the acceleration of due to the earthquake. However, if it's traffic, we will have, the loads of the traffic. It can be, road traffic or railway traffic. So, for example, here we had some studies to deal with traffic-induced vibration and how we can mitigate that. And we were looking for discontinuities. For example, you put a trench or you put a very stiff barrier, a concrete barrier, because if you have sensitive equipment, for example, in your structure, you don't want that sensitive equipment to be influenced by traffic either from the surface or traffic from a tunnel, for example. So that's an example of modeling. And in this case, it's a soil structure interaction, because if you consider the structure, you cannot take into account, the vibration coming from traffic. So this is an example, but also we studied the difference between, a conventional embankment for railways and a geosynthetically reinforced soil with vertical walls for high-speed rail. And we used this model. Again, the loading is due to the train, but if it's earthquake, we can just change, the equations we are solving. So the mesh, the model, it's all the same. It's just the forcing term. We have to put, mass times acceleration due to the earthquake. I hope this gives, an idea about frequency domain analysis. And just to finish about frequency domain analysis, it's very quick. So 2D or 3D problems, they only take seconds or minutes to calculate, to simulate. So although they are complex to develop, especially the non-reflecting boundary conditions, but when it comes to simulating, it's very, very, fast. Now, very quickly, I'm going to present the time domain analysis. So time domain analysis, they are easy to understand. What we do, we mesh our domain into, finite elements. So here I present a 3D modeling. So inside the domain, it's known technology, it's finite elements. So we use brick elements, linear, quadratic, etc. But the challenge is again on the boundaries. So the boundaries, we need to have proper non-reflecting boundary conditions. So for example, in Abacus, we can find infinite elements, but also the Lismer and Kuhlmeier absorbing boundary conditions. These are just like dampers. So these dampers, when the wave reaches, the boundary, we put a damper there where, the force of the damper is proportional to the velocity reaching that boundary. Radical velocity, what type of velocity to take? So for example, here I'm giving just a 2D configuration. So for example, here, if we have waves, coming, from infinity, reaching this, element, so the vertical force will be linked to the pressure wave, and the horizontal force will be linked to the shear wave. However, for this, it will be the other way around. The vertical force will be linked to the shear wave, and the horizontal force will be linked to the pressure wave. So it's really easy to implement these ones. They act on the velocity at the nodal point on the boundary, and we can put them on all lateral boundaries, but also we can put them in depth as well on the base. So if the base is fixed, that's it, it's just zero displacement. If it's not fixed, we can put these dampers there. And then for time stepping, it's a very long simulation, because what you have to do, you have to iterate if it's explicit time stepping. So you have to calculate things at T1, then move to T2, T3, etc. The problem is usually the elements, the finite elements, they have to be really small, very, very small. So if you want to capture a high frequency, so really you need to put your elements very small. And then if the element is very small, the consequence will be your delta t, your time step, must be even smaller. So usually we are talking about 10 to the power minus 5 of a second. And then if you have to, for example, just simulate 1 minute or 2 minutes of an earthquake, let's say 1 minute of an earthquake or even few seconds. So every second will be divided into 100,000 time steps. So, and if you are talking about 60 seconds, you have to multiply that. Then for each time step, you have to deal with a 3D model. So it means it's a huge, it's a huge matrices, and therefore it takes really long time. So really in the frequency domain analysis, it's fast. However, in the time domain analysis, it's lengthy. Computationally, it's very, very expensive. So, for example, this 3D model, just to show very quickly what we do to validate the model. So, for example, what we do here at the top, we just took a static problem, Bussinesque problem, and then we solved it in time. Okay, so although it's static problem, we can solve it in time. We do a time marching, time stepping, and then we can check. It leads to similar results. Of course, for Bussinesque, it's semi-infinite medium. Here, obviously, here it's a finite medium, but we put non-reflecting boundary conditions of this type, Leisman and Kuhlmeier, to mimic the infinite medium. So that's a kind of validation. The other kind of validation, we take a soft soil layer overlaying bedrock, and then for that, we know that it has a fundamental frequency. For example, in this case, we choose the parameters to have a fundamental frequency of 10 hertz. And then what we do, we put a Dirac impulsion. It's like a small impact there. And then with a certain frequency. And then we look at the displacements at the surface. So, for example, at 5 hertz, you can see these are the displacement. Then 10 hertz, when it coincides with the cutoff frequency, we can see it leads to resonance. So the displacement, they keep increasing. So if we continue, they keep increasing, leading to very large displacement. But then when you move to higher frequency, for example, 15 hertz, we see that it's vibrating normally and it's not leading to resonance. So that's a way to validate it. Then when we take the displacement, we apply FFT, we find again, the 5, 15 hertz, but we look at 10 hertz and we see that it leads to the largest displacement, reflecting, this cutoff frequency. So that's a way to validate that 3D model. So last, I'm going to show just a few examples how we use this model. Again, I didn't have the chance to use it for earthquake, problems, but I used it for railway traffic problems. So in the UK, they are building a high-speed line, but they don't want to face problems which were faced in Sweden. They are called critical velocity issues. And I will explain it in a moment, what's critical velocity issue. In fact, if we know earthquake engineering, if we know the waves in soils, it should be easy to understand that critical velocity issue. So again, the model can be used for earthquake analysis, soil structure interaction. It's just a matter of changing the forcing term into mass times ground acceleration. Okay? However, here, because I'm dealing with railway traffic induced vibration, I use the loading coming from the train. Okay? So you can see here, it's 3D modeling. So the elements are volume elements, 20 node brick elements. They are quadratic displacement variation. And what's critical velocity? I'm sure you all know for supersonic flights, when the flight, approaches the sound speed, you get a sonic boom. So that's due to the fact that the plane is approaching the the speed of sound. Un problème supersonique donc تكون طياره هذيك تكون يعني تمشي بسرعه هذيك السرعه تقرب السرعه تاع الصوت واذا تقرب السرعه تاع الصوت ولا ديباسي السرعه تاع الصوت يكون تما السونيك بوم. فحتى في الارض حتى في السويل it's the same problem. If the train or the moving load goes on soft soil معناتها rally wave speed is low, لا فيتيس تاع لي زون دو رالي حابطه شويه، دونك لو تران يقدر الا كان تران غروند فيتيس تقدر هذيك لا فيتيس توصل ولا تقرب الرالي ويف سبيد. اذا قربت يكون عندنا لو ميم فينومين ويسموه جراوند ماك كون. دونك في السماء يكون هذاك لو ماك كون تجي الاخر الطياره هذيك تقرب لا فيتيس دو سون. نفس الشيء يعني في السويل اذا كان موفينغ لود يقرب لا فيتيس تاع لون دو رالي يكون عندنا جراوند ماك كون. وكي يكون عندنا جراوند ماك كون معناتها فيري لارج ديسبيسمنت، وبيان سور هذا ترى اذا كانوا فيري لارج ديسبيسمنت كان ليد تو deterioration of the track. يقدر it can lead also to derailment and accidents. So here, for example, we use that model. We have a conventional speed. So it's stiff soil. La vitesse de l'onde rallye طالعة بزاف. Donc هاد la vitesse حابطة عليه. Donc it's very low. So it doesn't lead to any problem. So we check that. So we use just one coach, and it shows normal displacement. There is no problem, no ground Mach cone. However, لو كان نبدلو هذاك لو سول ونديروه soft soil, in this case, so it's a train on soft soil عندنا critical velocity effect وهاوليك the ground Mach cone how it's developed. The displacements, they start to become large, and because the train speed is approaching the rally wave speed or the critical velocity for this track, so we can see the cones developing here, okay? And we get very large displacements. So for example, in this case, 2.5 millimeter, and I know for HS2 in the UK, the tolerance must be 1 millimeter. So it's too high for that. And it means that the track will be fatigued very quickly. And if, the displacements are large, it means the track will lose its geometry with time, and it can lead to problems. So what we did, we simulated a critical velocity effect with artificial bedrock. So نقصنا من هنا it had a certain depth. We assumed to reduce the depth and there is a bedrock. If you do that, only the high frequency will propagate. The frequencies below the critical frequency, they're not going to propagate. هذا أمر معروف في geodynamics. We can see, although there is a Mach cone, it's only the high frequencies which propagate. High frequencies, it means low wavelength. So it means they don't propagate a lot in the soil. And the displacement is reduced to 1 millimeter. But also what we can do, we can stiffen the soil. فمثلا it's another model. What we do, the soil was soft and we had critical velocity issue. So what we did, we stiffened the soil. For example, we can put lime and cement columns, for example. That's the solution adopted in Sweden. The site it's called Let's-Guard. So what they did, they just put stiffening of the soil. So if you do that, you reduce the effect. فمثلا هنا كانت لا فيتيس دو تران قريبه بزاف لا فيتيس دو لون دو رالي، بصح كي درنا ستيفنينغ اوف ذا سويل طلعنا ستيفنس تاعو، معناتها طلعنا لا فيتيس دو لوندورالي، معناتها هاد لا فيتيس هذه ولات بعيده عليه. اي دونك دون سو كا ما كانش ليفي تاع جراوند ماك كون، ونشوفوا لي ديبلاسمون يسون انفيريور ا 1 ملم. Okay, Akh Mohammed, I finished. I'm going just to conclude. I kept it very simple, very general. The tools I presented here, they can be used directly for earthquake engineering, soil structure interaction. Unfortunately, the applications I showed, they are soil structure interaction, but not applied to earthquakes. They are applied to traffic-induced vibration. فبسرعة, soil structure interaction has no significant effect, can be neglected in certain cases, small structures, stiff soil, half space. However, it cannot be ignored in case of heavy structures. وها هي heavy structure, for example. I interact with a principal engineer from Atkins, and he works on Hinkley Point C nuclear power station. This is just a schematic diagram of this nuclear power station, and this is how it compares to a structure of 6 floors. Okay, so it's huge, and this is what we call heavy structure. So this heavy structure will definitely have an influence on the soil, and in that case we need to take into account soil structure interaction, but also if we have soft soil, layered soil, steep change in stiffness, إلى آخر ذلك. I showed that numerical modeling using frequency domain analysis, if we manage to do non-reflecting boundary conditions, it's easy. It takes short time, it takes seconds or minutes to simulate the problem. However, if you use time domain analysis, again, if you put the non-reflecting boundary conditions, for example, in this case, we put dampers, it's fine, it works, but it takes very, very long time. So the examples I showed here, they take 3 weeks, for example, to finish on a very good computer. So that's a long time. So it means you spend time developing your model, and then after that, for each parameter, you have to wait 3 weeks, 3 semaines, pour obtenir le résultat. It's a long time. So every method has its benefit and disadvantages. So I hope I gave a summary, a good idea about soil structure interaction. As I mentioned, the tools can be used for earthquake engineering, but here I use them for traffic-induced vibration. I finished, Akh Mohammed. Shukran.
Barakallahu fik, Ustad Omar. Thank you very much for the very insightful presentation and lecture. Actually, that was the objective. الهدف تاعي من when I invited you to give this lecture is to lay foundations of the numerical simulation, because I think it's a discipline that start to gain much more interest because of the computation power. We are getting faster and faster computer, and as you said, it's time-consuming process that can take up to hours and days. I personally myself used a lot of simulations for numerical for earthquake. استعملت finite difference method, and I also had to deal with the absorbing boundary condition and buffering, and I spent a lot of time coding this. So I'm happy to see that this is a problem that is tackled by many scientists all around the world. على بركة الله, we'll take some action, some questions from the Q&A from the comments. We have so many questions today, so thank you very much for all your questions. I will try to pick a few of them. So the first question is, can't we just dump the soil with a material that can dissipate or absorb waves? We can connect these dumped materials so we can deviate them away.
Yes, so I believe when I see this question, I remember PML, perfectly matched layer. So what people do, they take their computational domain, and then on the boundary they put it's like they take a soil and then squeeze it, but they put very high damping there. So it means when the waves come there, they are sharply damped, and if the energy is dissipated, it means very little will go back, or probably nothing will go back. Yes, that's fine. if this is the kind of absorbing boundary condition, yeah, it's fine. PML works really fine, but it's not easy to code, to develop, to implement. So people, develop different kind of PML. If you use certain kind of finite elements, linear, for example, for certain problem, acoustic, so you have to develop the PML. If you use it for elastic problem, you have to develop the PML. If you have rectangular geometry, you have to develop the PML for that. If you have circular geometry, you have to develop the PML for that. So it's not off the shelf. You cannot use a code and say, oh, I use PML for this one. You have to adapt it. Yes. However, if you mean by this question to increase damping in your soil, and then the waves, they are damped because of the high damping, and then they are reflected, and because of the high damping, when they come back, they lose energy as well. That's not realistic, because you have to put the real damping of the soil to model the real behavior.
Thank you very much, Professor, for your answer. We will pick up another question. Is it right that working with fixed soil system is the most conservative case for designing a structure?
Yes. So you mean if we have the structure, usually in design offices, the first thing they do, they only take the structure, they fix the base, and then they use the available methods. So I think we have to think case by case. So it may be conservative, so it means you will over-design your structure, or you may miss something and then you design your structure like that, and then when you study it with soil, interaction, you find out that it's not the same behavior, and your structure is not going to withstand the earthquake. So saying it's most conservative, I'm not sure, because dynamics, it's all about frequency. So if you have a tower, for example, which is highly dynamic, it can catch different modes. You put it on fixed boundary, and then in a different study you attach a chunk of soil to represent soil. Yes, probably it's when you fix it, it may be most conservative, because when you add the soil, you are really increasing damping, and you are elongating the period. So it may be most conservative. But as a summary, I think it's case by case. We have to look at the problem. Is it justified to consider fixed base, or is the soil structure interaction important? And the best is to deal with both and to show that there is difference or there's no difference.
Thank you very much, Ustad. Another question from the same person. How much is the Slender limit to include soil structure interaction in the analysis?
Yes, I think when we teach earthquake engineering and we talk about H and B, so H is the height, B is the base. Usually H over B less than 5, so it's not slender, but above 5, it's approximate. Above 5, it's considered to be slender. So if it's not slender, the dynamics may be just restricted to the first mode, and therefore you can approximate it to a linear variation. But if it's above that, it's likely to catch higher modes, and therefore I think slender. Again, if you work in a company, you may talk to the colleagues, to the boss, and they may tell you what's slender for them. But from what I saw before, it's like H over B above 5.
Thank you very much, Ustad. We take another question. So using a discretized model, we'll need to introduce the right parameters of the soil. How a saturated or unsaturated or cohesive-less soil affect the mathematical calculations?
Yes. See, all the computational models we develop, they are all approximate. and we try to describe the real problem. But really what you have in the computer, it's what's in your mind. It's not really what's in nature. So usually, you know, for example, for frequency domain analysis, we are only taking the Young modulus, the Poisson's ratio, and the density, and that's it. However, if you go to time domain analysis, I think it gives you more flexibility to introduce other parameters. So, for example, for the constitutive models, there are hundreds of constitutive models where, for example, saturated, unsaturated can be taken into account. So, but in that case, we need to move to nonlinear transient analysis. And I mentioned earlier that already linear transient analysis takes a long time. So just because of the fine mesh grid, the small time steps. But now, if you introduce nonlinear, because of these parameters you mentioned of the soil, because the soil is the most complex, the most complex material. If you add that, so you will have nonlinearity. So it means for each time step, you will have to iterate, and then once you converge, you move to the next time step. So it means you are making even your simulations very, very, very long. And I think in practice, in industry, they always think about what's the best compromise. When you design, you over-design a little bit anyway to be on the safe side. So they can afford, for example, I know they can afford, rather than go to nonlinear, they take equivalent linear. So for example, in the case of earthquakes, because there is soil, they increase damping and they reduce the stiffness. And I think this will represent the nonlinear behavior, but they carry out linear analysis. So really, including saturation, cohesion. From the academic point of view, I think it's good for research, but I think in industry, I think they have their own practices.
Thank you very much, Ustad. I think there is another question which is related to what you are discussing now, is about the non-linearity of the soils. If you have any additional comment, dear professor, question is: when considering SSI for seismic analysis of structures, the behavior from very soft soil to dense soil is not linear. Soft soil behavior better than dense soil, and vice versa. So I think, yeah, this is the comments you were just discussing right now in your answer. So I will take one last question, and from the Q&A session. What is the name of the program you use to simulate waves propagation on the soil, stiff or soil under the railway?
Okay, so we have Abacus. So currently we are using Abacus. But Abacus, you need someone who knows it really well, because it's a big beast and it has infinite elements, and it has the dampers of Lismer and Kuhlmeier. The problem is that we get PhD students, they work 3 years, but when they become experts, they finish and they go somewhere else, and you get someone else new, and they have to learn and they spend time. And then when they get experts in that, they finish and they go. So what we ended up doing, we have our own codes. So for example, in time domain, we developed this 3D. So the simulations I showed for the trains, it's a code called DAT3D. So it's just, it's dynamics in three dimensions. But also we have our own problems. So it's our code, we developed it at Heriot-Watt. And in frequency domain, it's called POS. And it's POS, it's Propagation des ondes dans les sols, just because I started developing that in France. So we kept that name. So POS, I can share it, it's not a problem. But that 3D, unfortunately, I cannot share it now. So both codes, they are, home developed. They are developed, by us. But of course, if we want to use commercial software, we have Abacus. Again, Abacus, you need experts in it. The problem when you develop your own codes, you have to manage the versions. So you keep developing, and then after few years, you have really to be good in managing the versions. Otherwise, you will lose a lot of knowledge, a lot of expertise.
Thank you very much, Ustad. Barakallahu Fik for handling the questions. We had so many questions today, so we pick few of them that I judge that most important to answer. So thank you again, everyone, for your participation. يعطيكم الصحة اللي قعدتوا معنا jusqu'à ce moment-là. Voilà, donc I think it's time to close this call. I would like to thank very much Ustad Omar for his very generous contribution to the project Earthquake Hazard Mitigation, where we shared basics and fundamentals of numerical modeling with the specialized and especially non-specialized audience. Inshallah, I hope this triggered interest for you to learn more about numerical modelings, because it can bring a lot of answer, and especially that there are many open source codes, whether it is FEM or FDM on the net. You can find in GitHub many open source, inshallah, and you can start use them in your own research في الجزائر. بارك الله فيك encore une fois أستاذ, يعطيك الصحة, شكرا جزيلا. نقول لكم inshallah we will meet again for next month. We will have another panelist for our project Earthquake Hazard Mitigation. Our next keynote speaker is going to be the Dr. Laghrouche, who is a researcher at the CGS, and he's going to discuss about the shaking table, the earthquake shaking table experiments in the CGS. Again, thank you very much, and keep in touch, inshallah. Stay in our INAS webpage, and looking forward to see you again. Assalamu alaikum.
Shukran. Assalamu alaikum.
Salam.